minus cos 2 theta. First of all, putting the upper limit, and then difference, taking the difference and putting the lower limit. This is again important formula whenever you are solving the integration. So I square equals to im square by 2 pi. Instead of 1, we can write that theta minus cos 2 theta. The integration of cos 2 theta is sin 2 theta by 2. Limit is 0 to pi. So here we are just removing the sign of integration and putting the by taking the integration of 1 and cos 2 theta. Now putting the limit of theta minus sin 2 theta to, first of all putting the value of higher limit, that is pi, and then after the 0. So I square equals to im square by 2 pi into pi, because as I already told you that sin 0, sin pi, sin 2 pi, sin 3 pi up to sin n pi all are 0. So the value of sin 2 pi or sin pi is negligible, or it is 0. So we are just getting that im square upon 2 pi into pi. Now pi is cancelled out, that's why I square equals to im square by 2. Now if we have to just remove the square of the left hand side I square, then we have to put the square of right hand side. That's why I equals to under root of im square by 2. Now if you have to just change, if you have to taking the im square into im, then you have to just convert that root into the 2. So IRMS equals to im by root 2, and this is our main root mean square value or main derivation of root mean square current. So IRMS equals to 0.707 into im. 0.707 is the value of 1 by root 2. That's why here we can prove that the value of IRMS equals to 0.707 into im. This is very important formula and many times asked in your exam. So just sincerely go through it. The next question. Obtain the line and the phase value of the current and voltage relation in 3-phase star connection. This is again important question and already 5 to 6 times asked in your GTU exam. First of all, just go through different terminology of the line voltage, phase voltage, line current and the phase current. The voltage across the two terminals of any one winding is known as a phase voltage, whereas the line voltage, the voltage is generated between any two consecutive transmission line is known as a line voltage. Like the line R and Y, so the voltage generated between the line R and Y, that is VRY. The voltage is between the line Y and B, that is VYB, and the voltage is between R and B, that is known as a VRB. So between the two consecutive transmission line, the voltage is generated known as a line voltage. The line current, the different three lines A, B, C, or you can say that R, Y, B. So whatever the current passing through that R phase, Y phase and B phase, or R line, Y line and B line is known as a line current, and whatever the current flowing through the phase is known as a phase current. There is no such a vast difference between the line current and the phase current. So whatever your phase current, that becomes your line current. But friends, keep in your mind the types of connection, whether it is a star connection or whether it is a delta connection, because the relationship between the line current, line voltage, phase current and phase voltage are differ in star connection as well as in a delta connection. So many times students may get fault to understand between the difference of the star connection and the delta connection. So you have to just keep in your mind. Now first of all, the relationship between the line voltage and the phase voltage in a star connection, as we already talked about that, the line voltage is root 3 times higher than the phase voltage. So you can write like that, VL equals to root 3 into VPH, or VPH equals to VL by root 3. In a star connection, the line current, that is IL, equals to phase current, that is IPH, or IPH equals to IL. Friend, here I am just giving you one difference of star and delta. First, VL equals to root 3 times VPH in a star connection, whereas VL equals to VPH in a delta connection. So in star connection, your line voltage is greater than √3 times greater than your phase voltage, but in your delta connection, your line voltage is equal to your phase voltage. And this is the relationship between the line voltage and phase voltage in star connection, and line voltage and phase voltage in a delta connection. Now the relationship between line current and the phase current. Your line current is equal to your phase current in a star connection, but your line current is √3 times greater than your phase current in a delta. So you can observe that they are cross connection with each other. Whatever the value of line voltage and phase voltage in star connection, that becomes your line current and phase current in delta connection, and whatever the value of your line current and phase current in a star form, that becomes your line voltage and phase voltage in a delta connection. So you have to just by making such kind of configuration and remember this thing in your exam. The power consumed in a star connection, that the power consumed in a star connection and in a delta connection both are same, so there is no need to worry about that. This is a 3-phase connection, that's why by taking the factors is 3 instead of in a single phase, that is a 1. So P equals to 3 into power consumed by each load. So we can write like that, P equals to 3 into VPH into IPH into cos phi, because this is a radian quantity, that's why we have to just taking that cos phi. So P equals to 3 into VPH. Now VPH is 1 by √3 VL into IPH equals to IL into cos phi. So by writing like that, P equals to 3 by √3 VPH IPH VL IL cos phi. Now by taking that 3 equals to √3 into √3, so √3 are cancel out, so we can write like that, P equals to √3 into VL IL cos phi. This is the power consumed in a star connection. Now there is a 3 types of power: active power, reactive power and apparent power. So this is a different active power, that means P equals to 3 VI, that is no any radian quantity. Then after the reactive power, that is a sine quantity, and then after the apparent power, that is a cosine quantity. You have to just remember these 3 powers in a star connection and a delta connection. Now the relationship between a voltage and the current in a delta connection, as we already explained in a difference form, so just quick go through that one. Line voltage equals to phase voltage in a delta connection, VL equals to VPH or VPH equals to VL, but there is a greater line voltage is greater than √3 times into VPH in a star connection, and line current is √3 times greater than your IPH, or IPH equals to 1 by √3 into IL. See, this is a power consumed by the delta connection. This is again the P equals to √3 into VLIL cos phi. So whatever the power is consumed in a star connection, that becomes your power is consumed in a delta connection. This is a important example. This is also asked in your GTU exams 3 to 4 times. A balanced 3-phase load 6 plus J8 is connected in a delta as well as the star across the 250 voltage. So 250 is a supply voltage, that is your line voltage. Whatever your supply voltage, that becomes your by default line voltage. 50 Hz, that is your F frequency, 3-phase supply. So calculate for both the cases, for the star and for the delta, phase voltage and phase current, line voltage and line current, and the power factors. First of all, if any examples given to you, you have to just find out whatever the data is taken from that example. So first of all, the ZPH, that is a load 6 plus J8 ohm per phase. VL, whatever your supply voltage, that becomes your line voltage, that is VL equals to 250 voltage and F equals to 50 Hz. So by phase voltage, first of all finding for the delta connection, your line voltage is your phase voltage. So your VL equals to 250 voltage. So your phase voltage VPH is also become your VL equals to 250 voltage. So this is a directly this is a quantity which we already directly proved from the VL. Now impedance per phase, that is ZPH. The equation for ZPH equals to under root of R square plus XL square. Now R plus XL, that is a real and imaginary part, that is finding from the load, that is 6 plus 8J, where 6 is a R and 8J is your reactive real quantity, that is 8J. So this is our XL. So by putting the value of 6 and 8 into the equation of under root of R square plus XL square, we can prove that ZPH equals to under root of 6 square plus 8 square. Now 6 square is 36 and 8 square is 64. So by taking the 36 plus 64, that is 100. So by taking the under root of 100, this is 10. So we can find that ZPH equals to 10 ohm per phase. Now the phase current, that is IPH, I equals to V by R. But for the 3-phase circuit on the polyphase circuit, instead of writing the R, we can put the impedance, that is Z. Z is nothing but the 1 by R. So IPH equals to VPH by ZPH. So VPH is our line voltage, that is 250 voltage, and ZPH is our 10. So 250 by 10, that is IPH equals to 25 ampere, that is phase current flowing through that delta connection. Your line current, that is IL equals to root 3 times IPH. Now IPH is 25 ampere, so putting the value of IPH into that equation, IL equals to root 3 into 25, root 3 into 25, that is a 43.30 ampere. So that is your line current in a delta connection. The power factor, that is cos phi equals to R by Z. R is a 6 that we already finding from the reactive part of the load, and Z is the impedance per phase, that is 10. So 6 by 10, that is a 0.6 lagging. Keep in your mind here your power factor is lagging. Now your active power, that is P equals to root 3 into VL IL cos phi. Putting the value of VL IL and cos phi, we are getting the active power, that is P equals to 11250 watt. That is your active power which is consumed in a delta connection. Now same we have to find out for the star connection, that is a phase voltage, that is VPH equals to root 3 times higher than your VL, and your VL is 250. So by taking the VL 250 by root 3 equals to 144.337 volt per phase. Friends, that is the 144. The voltage in a phase voltage in a star connection is decreased than in a delta connection, because in a delta connection your phase voltage is 250 voltage, but in a star connection your phase voltage becomes 144. Now the impedance for phase, that is ZPH equals to R square plus under root of XL square, that is a same equivalent to the in a delta connection. So ZPH equals to 10 ohm per phase. The phase current, that is again IPH equals to VPH by ZPH. Your VPH is equals to 144.337, your ZPH is 10. So by putting the value of by taking the ratio of these two, we are getting the value of IPH, that is 14.43 ampere. Again the value of your IPH is increased than your delta decreased than your delta connection. The line current IL equals to IPH, whatever your line current, that becomes your phase current in a star connection form. So IPH equals to 14.43 ampere, so your line current IL is also 14.43 ampere. And the power consumed in a delta connection or in a star connection, both are same. So whatever the power factor in a delta connection, that becomes your star connection, that is 0.6 lagging. But your active power, that is P equals to root 3 into VL IL cos phi. Your VL and IL both are different than a delta connection, that's why the active power, the value of active power is also differ, that P equals to 3750 watt is active power in a star connection. So this is very important examples of GTU exam. Again we see that same example for the different changes, and this is also asked in your GTU exam. The question is that the three identical impedance of 8 minus 6 J6 are connected in a star across 400 volt 3 phase supply. So calculate for the both the cases phase voltage, phase current, line voltage, power factor, and the total active power. First of all, finding the data given to you, ZPH equals to 8 minus J6 ohm per phase, VL equals to 400 volt. Friends, again I am telling you that whatever your supply voltage, that by default becomes your line voltage, that is VL. Now the star connection only, we just proved that was the thing in the star connection only. Then for the delta connection you can already go through from the previous example, so you can just try for yourself to prove that for the delta connection. Here your R becomes the 8 and your XL becomes the minus 6. So by proving the value for Z, First of all, the for the star connection, the phase voltage VPH becomes the VL by root 3. So putting the value of VL, that is a 400 voltage, and root 3. So 400 volt by root 3 equals to 230.94 volt per phase. That is your VPH. Now your impedance per phase, that is ZPH, equals to under root of R square plus XL square. Now here your reactive component, that is 8, and your imaginary component, that is XL, is minus 6. So by taking the 8 square, that is 64, minus 6 square, that is 36, 64 plus 36, that is 100. So by taking the under root of 100, that is again the 10 ohm per phase. So ZPH is nothing but the 10 ohm per phase. The phase current, that is IPH, equals to VPH by ZPH. Though putting the value of the VPH and the ZPH into the equation of IPH, that is 230.94 by 10. So we get that IPH equals to 23.94 ampere, and whatever your line current, that becomes your phase current. So here we are just proving that the IPH equals to 23.94 ampere. So that becomes your line current, that is IL equals to 23.94 ampere. Now the power factor, that is cos phi equals to R by Z, that is 8 by 10, that is 0.8 lagging. Again, this is below the unity level, that's below the level of 1, that's why it is a lagging, and 0.8 lagging. And the total active power, that is P equals to root 3 VL IL cos phi. Putting the value of VL and IL and cos phi into the equation of P, we are getting that 12,800 watt, that is total active power. That is a very high active power for the star connection if you are giving the line voltage is very high. Now compare the two circuit, the series resonance circuit and the parallel resonance circuit. Here we have to just compare some of the parameters of the series and the parallel resonance circuit. There are 9 to 10 parameters. The first parameter is the circuit type. The series resonance circuit is a purely resistive circuit. It means that here no any inductive component and no any capacitive components. Only the component is the resistor. The parallel resonance circuit is a purely resistive circuit. This is again no inductive component and no capacitive component. The power factor. In a series resonance circuit, the power factor is unit, whereas in a parallel resonance circuit, the power factor is also a unit or unity. That is it means that it's a 1. The topic next one is a impedance, that is Z. For the series resonance circuit, your impedance is very minimum, that is Z equals to your R. Whereas in your parallel resonance circuit,